recording. Everybody in here could see. Well, my wife got another snow day from work today. That's two, because she works as a remote developer in Illinois. In downstate Illinois, they got like, I don't know, 9 feet of snow. and it's still coming down. That's got to happen more and more. People working remotely, people like living in tropical like climates, and you get snow days. All right. So it works out doubly for her because she works at home here, but she doesn't like go out a lot. She's kind of a recluse. So when we have a legitimate snow day here, when they wouldn't get one there, doesn't impact her hardly at all. Maybe it delays a trip to Meyer or something. But when they get one there, it just impacts her where she doesn't have to work. But the work still needs to get done. So then you just fall behind on your projects, which kind of sucks. Like the deadlines seem to not move. Okay. So for today, we were to look at the differences between threads and processes, right? What did we come up with? If you were to give me kind of a highlight reel of threads versus processes, what would you say? Go ahead.
Processes can be multi-threaded or single-threaded, and single process is one thread.
Okay. That's probably so. So what he said is that processes can be single-threaded or multi-threaded. So that's probably the way modern day processes are implemented, because all of our operating systems today are thread aware. So they actually implement processes on top of a thread, where your default process would have a single thread of execution. That guy would be like the historic just process that magically runs on the CPU. Okay, however it accomplishes that. Okay, so that's a fair enough thing. I guess I'm looking for what are the differences between these two guys, maybe from an operating system perspective. So let's keep going. Go ahead.
A thread is spawned by a process, and each thread has its own stack, but it shares the same as process.
Okay. So threads, I'm going to say, are lightweight processes. Processes are heavyweight. All right. And then you said that a thread gets its own stack, which is interesting enough, I guess, not overly important for us in the details, but shares the heap of the parent process. All right. So if we're going to take that one step further, we might say that threads share the CPU time with the parent. So a parent, this kind of goes back to what are the services an operating system provides for us. One of those services is process management. And typically, and very related, is processor CPU management. So it's in charge of keeping the CPU, probably, especially today, multi-core CPUs, as busy as possible. The goal of the operating system would be to have the processor busy 100% of the time. That's typically not the case. I think if you look at most of the statistics, your processor remains idle 96, 97% of the time. So it's pretty, when you go and spend a bunch of money on processors, unless you're using it for a very dedicated task, you probably didn't need that high end of a processor. But in any case, so threads do share the time with the parent process for how much CPU time they get. So if you have a parent process that gets 5 seconds of CPU time, just using big numbers, and it spawns off 4 children. Each one's going to get 1 second, including the parent process will get 1 second. We're going to say that that's a relatively good thing, because the antithesis of that is a process gets its own amount of CPU time. Now, we saw last time, or at least we said it out loud. We haven't programmed it yet. We haven't seen the fork system call do anything yet. But the idea here is that it's actually quite easy in C to just create a child process. If we want to see that real quick. We just do a fork C example. This will probably have a nice short. All right, this will. All right. Now I'm going to have to. I'm going to tell it to sleep here for a second. See, sleep function might be in time.h. Oh, no, it's in there. So I just need to do milliseconds. I think that's number of milliseconds. Nope, that's the number of seconds. So we're gonna. And actually, I'm gonna put this afterwards. Okay. Yeah, the reason if I don't put the sleep in there, we only got one of them. I'll explain that in a second. And that's more of how online GDB works. Once it gets to the end of the original parent process, it just kills it all off, including all the threads. But in any case, nice short program here. Here's the fork system call. I'll just go ahead and say int PID is equal to this. And I'm going to say all right. So here's our fork system call. We're actually going to be doing some other stuff before it, but this just kind of explains our difference between threads and processes. So we see how easy it is. Just calling the fork system call literally duplicates this program. You get a brand new heavyweight process, not a thread, but a brand new heavyweight process. So we now have 2 different processes. And we see here's one of the processes displaying hello world, followed by the process ID of that process. And then we have another process that's displaying hello world, and it's showing the process ID of that guy. That is the value that fork returned to this. If you're the parent, you get a 0 back. That lets you know I'm the original. So a lot of times after the fork system call, we would ask the question like, if PID is equal to 0, we might say parent, else child. Maybe we'll say this is put your parent logic in this area, child logic in here, regardless of which one they're going to sleep for a second. All right. And you're not necessarily guaranteed what order they come out of here in. because that's part of the scheduling of those processes. Go ahead.
So is it when you force this contract, is it creating a
yes, it's a brand new program that's running, but it picks up right after this line. It doesn't start over. Yeah. So after this line, we have a new process that that is identical up to this point. So it's a duplicate. And then continues below. So it doesn't go back up to the beginning of it and start running again. It just picks up where you left off, but what was 1 is now 2. Actually, did I mention the show called Counterpart that I've been watching recently? It's effectively a TV show that's equivalent to the fork system call. It takes place in like Berlin, Germany, for 2017 to 2019. Some good actors are in it. It's called Counterpart. I think it was on Prime Video. But in Berlin, something happens where the Earth duplicates, and underneath this building, there's the crossover point where if you walk one way, you're in the building, the same building in the other Earth. But it was identical up to that point, split, and then that's when things maybe started diverging. Fascinating show, but in any case, that's somewhat related here, I guess, in a loose way. But understand here that after that line, we now have 2 processes. We have the original, and then we have the child. Then we can ask a question. If I'm the original, if the process ID that fork gave me was 0, he lets me know that I'm the original, and I'll keep going. Otherwise, I must be the child. So this would be where they diverge. If you were doing systems programming using the fork system call, you would say, oh, the parent's going to keep doing this stuff. The child might go on and do this stuff. Does that make some sense? All right. So we see how easy it is to create a whole nother process inside of a C program. Now that kind of becomes dangerous as well. From an operating system perspective, what is a PID? What is that guy? What is he used for? Go ahead. Okay, so process ID, what are they used for? Okay, so it uniquely identifies a running process on an OS. Okay. How many? Go ahead.
Is it completely unique, or is it just like when you run that C program, the parent is 0?
But the parent isn't 0. The parent actually does have a process ID. Here, I could show you. My parent is it get parent process ID? I think it's that. Yeah, so the child has 938. The parent's PID is 933. Yeah, so let me do this. Actually, I'll do it up here. So the parent will get his own PID. The child will get his parent PID. Oh, the child actually got his parent's ID, not him. So that means the child would need to use get PID to get his actual . So this is the child process ID. And this is the, and his parent is 2509. Actually, that is weird. Why are they different? Parent logic says, this is the process ID fork return for me, which is 0 if you're the parent. So here's the fork system call. Oh, it's a value of 0 to the child. Okay. Let me just put that. Well, let's make a slide for it, just so I get this right for the notes. Fork returns 0 to the child. So if we were going to update our code here, this is actually the child logic in here. And the child's process ID would be get the result of get PID. And then the child has a parent, and the parent's process ID would be the get PPID. So that'll be the parent's process. Else, this is the parent logic, and the parent should have its own process ID, which should match this guy's PPID. Let's make sure that's right before I. So here's my parent logic. Parent says my process ID is 1183. Here's the child. The child says, okay, my new process ID is 1187. I was just born. And oh, by the way, my parent is 1183. Make sense? So fork actually returns a 0 to the child, letting him know if he's a clone. And the parent just to kind of go back in here. New child should be PID. Yeah. So now you see, this is the parent's perspective. The parent gets their own PID and says, oh, I'm 795. The result of the fork system call to the parent was the new process ID that was created when it made the child. So the parent knows about the process ID of its child. It gets that as a result from fork. The child, it gets a 0 returned by fork, letting him know he's the clone. The child can get his own process ID using get PID, and that's a 799, which matches the parent's understanding of who the new kid is. And then the child can also look up who their parent is using get PPID, which says he's 795. So these two processes can find out information about each other, which is going to be helpful to us later on when we start trying to communicate between processes. We're not quite going there yet. So get PID returns the process ID of the running process. Get PPID returns the process ID of the parent process of the running process. Interesting thing here, let's make sure that it gives me the value I think it's going to get me. I'm the parent. The parent's parent is who? Who do we suspect it might be? Go ahead. Okay. But is the user a process? Go ahead. It'll be what? Probably not the web browser, because this is running. I mean, the web browser is just presenting the output. This is actually running on a Linux terminal somewhere. Who runs this program? The operating system. So the parent's going to be the process ID of the process that launched this program, which my guess is it's going to be the process ID of the bash shell that actually launched this program. But the concept is going to be whoever the operating system writer, whatever they decided is the parent process. It may also get PPID might be implemented in such a way that it'll return like a 0 or a -1 if it's already at the top. Like, you don't have access to your parent. Your parent is, you know, something from the administration side of things. But let's just see what it gives us for the yeah, so we get 3688 is the parent, which is a process ID. We don't know who that is at this point. We can actually look it up based on my the next thing I'm going to do. Will remind me when we get to using exec. We can go and actually issue a command to the underlying operating system to allow us to see who actually is the owner of that. My guess is the bash shell. All right, but interesting enough stuff there. So back to this slide I was working on. It's asking what's a process ID. So this is something that uniquely identifies a running process on a computer, right? That way we can, you know, the operating system, when it's scheduling processes for the CPU, it's going to say, okay, well, this process ID is going to get his CPU time. Now he has to pack his bags, get lost. And now another process ID gets his CPU time. So we're having to manage those process IDs. All right. How many process IDs can we have on an operating system at one time? What dictates that? You're the operating system writer, and you're deciding what are the capabilities of my operating system. What drives that your maximum number of process IDs you could possibly have on the computer? Well, I suppose possibly they could possibly say that they're going to allow a unique process ID that's up to the maximum size of a value that can be stored in memory, which would be gigantic. So probably not what they would do, but not necessarily a wrong answer. Highly unlikely. Go ahead. Okay, so what's a number? How are numbers stored inside of computers? Well, think about our primitive types in C. What are our various primitive types in C? Same answer is for Java, C++, whatever. What are our primitive types for integers? Go ahead. Int, okay, easy one out of the way. No, keep going. Primitive types for numbers. I'm only talking about whole numbers here. Strings aren't a primitive type anyways. No, not an integer type. Stored as a number, but not an integer type. I'm looking just for integer types. Whole numbers, whole sign numbers. Go ahead. Long. Big brother to an integer. What else? Go ahead. Short. Yep. Little brother. Hardly ever used. Last one. Double will be a floating point type. Go ahead. Well, in C, there actually is something called a long, but you know, let's keep. We'll just go with one more in here. That's not the one I'm looking for. No, it doesn't count. especially since you formed your answer in the form of a question. Yeah, you're it's a bad habit. don't do that in interviews. What's the last one? Go back to your 200 knowledge. The very first thing we looked at the primitive types. Yeah. Which one did she suggest? Well, those are two separate things. What's a bit? No, I mean, I'm asking the question. What is a bit versus a byte? Go ahead. Byte is 8 bits. Okay, and what's a bit? It's a single 0 or 1, right? Single 0 or 1 is a bit. A byte is 8 of those. All right. Does our modern day programming languages, do they let us store a single bit, or is our smallest data type the byte data type that holds 8 bits? Go ahead. I'm talking about the C programming language. Byte. So remember that slide where we had our primitive types? So we have byte, and this is a 8-bit signed number. So this is -128 to +127. And then we had short, which is a 16-bit signed number. So this is -32,768 to +32,767. Then we had int, which is a 32-bit signed number. So this is 2 to the 31st. So negative that to positive that. And then long is a 64-bit signed number. 2 to the 63rd power. That guy, I think that's 9.2. I think it's quintillion. I think is what the oh, did I? No, I don't think it will be that because the decimal point moves. So I just said -1. It's accurate. All right. Doesn't really matter what these numbers are, but hopefully this reminds you of a slide you've seen in the past talking about our primitive types, and you get in. So then we have char. Char is an unsigned number representing in C, it's ASCII. So it's an 8-bit unsigned. So that's 0 to 255 for the ASCII character set. In Java, it's actually a 16-bit for Unicode, maps to Unicode. All right. But the idea here is that these are our, if you're a operating system writer, chances are you've written that operating system in C. Pretty good chance. Okay. So you're going to be, these are the tools you have available to you. All right. These are your types. So the number of process IDs that your operating system is going to support is limited by which of these values you use as your counter, right? Unless you decided to go a little crazy with it and you decide, look, I'm just going to invent my own, something along the lines of like Java's big integer class, which just lets me have arbitrary size integers up to when I run out of RAM. But that comes with the cost of performance. So what we're really talking about here is our primitive type integer types that are kind of linked to the hardware itself. We have 8-bit, 16-bit, 32, 64-bit registers inside of our computers on the CPU. So having a very close relationship between those actual registers and these primitive types is pretty helpful for us from a performance perspective. So chances are the programmer or group of programmers that wrote the operating system, they had to decide how many process IDs do I want my operating system to uniquely support? And that drove them to, that made them pick which of these primitive types. Now, C does allow you to pick to flag any of these as unsigned. So you could say, I want an unsigned byte, which would be 0 to 255. Okay. Quick question, see how much you learned in 325. Why is this negative value 1 greater than the positive value? Go ahead. Well, that's okay. Yeah, you don't want to have 2 zeros. You don't want to have a positive and negative 0. But how are signed values encoded in our computers? Go ahead. Okay, if you did that, that's called sign and magnitude, but then you'd have 2 zeros. Yeah, you'd have a positive 0 and a negative 0. So the most straightforward, hey, this is our first pass at this. I want to store positive and I want to store negative values. We'll just use one of those 8 bits as either a 0 or 1 plus sign or negative sign, right? Okay, but then the problem with that, as you pointed out, is we end up with 2 representations for 0, a positive and a negative representation for 0. Go ahead.
Is having 2 representations of 0 bad, or is it just that
technically inefficient, right? With 8 bits, we have 256 unique collections of those bits that we can write. So to get the most bang for our buck, we should uniquely represent 256 different values, not the same value 2 separate times. So I don't know, let's say yes, it's bad, especially since there's actually another way. So how are these values actually encoded if we're not using sign and magnitude? You all had 325, right? Computer organization, you learned this in there. People are killing me. 2's complement. Remember, you didn't learn 2's complement? Oh, it's a phrase you've heard. Okay, so 2's complement, what you do is you go through, you flip all the bits, and then you add 1 to it. And that's the encoded version of a value. And if the far right bit is a 1, it's a negative value. The far right bit is a 0, it's a positive value. The negative values you have to decode to get back to find out this is the negative version of the original value. Go ahead.
What's the point of doing this instead of having unsigned
Well, you get 256 unique values here.
Yeah.
Isn't that 256?
Yeah. Is there any reason to do this instead of just having unsigned?
I mean, if you want to represent the number -5, then so if you need to do math with a negative number, you got to be able to hold the negative number. All right, so these are our primitive types, but like I mentioned, C does allow us to say, look, I want the full positive power of a type. So I want the entire 8 bits, for instance, to be unsigned. So then it would be 0 to 255 for the same reason, right? It's any way you cut it, you got 8 bits to work with. We have 256 unique things we can represent with those 8 bits. All right, 256 unique ways we can write 8 zeros and 1s. So if we're the programmer who is writing this operating system, we had to make the call. We had to decide which of these data types do I use to represent my processes, my process IDs. And that data type will be your upper limit for the number of unique process IDs you can have, right? Now, you might just say, well, why don't we just have a long for it? That sky is the limit, right? Well, you were starting to say at the beginning when we said what goes into a process versus a thread, the processes, and I mentioned they're heavyweight, have a lot of crap associated with them, right? So with each one of those process IDs, you have like a suitcase hanging off of it that takes up memory, that has stuff in it. So maybe 9.2 quintillion processes is an unlikely number of processes that are likely to be running at the same time on an operating system. regardless of what you could have running, right? Now, are we going to have more than 256 unique processes running on a computer at once? Let me have terminal open already. What is it? PS-AX. Pipe to count. I have to write our own program for it's called word count. So not word count. Line count. Okay. So it's that guy, pipe to WC-L. 891 processes running right now. All right, if you're looking for what this is doing, this lists all the running processes. The pipe command says, instead of putting that output to the screen, send that output as input into this command. The word count command with a flag of -L counts the number of lines in that output. So these are kind of like the ninja moves you can do with terminal commands. All right, so 891 processes currently running on this computer, right? Now, some of them, not a high percentage of those 891, are things that I launched, right? So my running applications. And some of those have multi-threads, multi-processes, so they're gonna, so we're taking up a couple more. But a lot of these are services provided by the operating system, other things that are running on my computer. Okay, but now if we're the operating system designer, we have to decide, well, how many unique processes might be running at one time? So we could say, well, there might be more than 256. Is there going to be more than 65,535, 536? Maybe, but now we're probably starting to get into that ballpark, or we might decide to call it quits. All right, maybe we jump to the 4.2 billion value, but let's just assume we're at the 65,536. So assume the operating system designer the OS designer decided to represent PIDs as a short. We'll say as an unsigned short. 0 to 65,535. So a total of 65,536 unique processes can be running at one time, right? What happens if you try to create a 65,537th process? Go ahead. Yeah, our world folds in on itself. Bad things happen, fails, crashes, whatever. You can't have that many unique processes because we're representing process IDs using a short, right? Okay, so we're going to be limited on this particular operating system that we're making an assumption about. We're going to be limited to 65,536 unique running processes. So we would say that it would be bad to have more than that. It would also be bad to just get up to the maximum number, right? Now, is it hard to write a program that creates 65,536 unique processes? Well, if you want to be more precise, for I equals 0, I is less than 65,500 and 36, I plus plus, fork, sleep for a while, you know, that way it doesn't end. You know, we want to take up that slot. Okay. This for loop right there, unless your operating system has things built into it to prevent a single process from creating too many child processes, which modern ones do. But that for loop right there has destroyed computer systems. Super short code that will generate, that will fill up that computer with a whole bunch of processes that are running for, I don't know, however many seconds this is, a while, right? Go ahead.
So, like, if this was to like happen, would the computer shut down and when you reboot it be fine, or would that be a problem? Just
when you rebooted it, would be fine because then all the running processes would have ended.
So, like before, like they fix this problem with modern operating systems, could be like an attack that won't be like
yeah, this was an attack. Okay. So you're attacking the OS, but here's the problem. I can go in and I can use the kill command. Kill command, I can give it a process ID and I can kill off that process, right? So potentially you can do, you know, list, use that same thing I just had before, that ps-ax, and get a list of all the running processes and, you know, kind of massage out the ones that are part of the operating system and just get the ones associated with this attack program and then just kill off all those, right? But what the problem is I don't even have the ability to launch a terminal because I'm out of process IDs. I can't get to a terminal to kill off the programs that are preventing my operating system to create any new programs. So you would have to shut down the computer. Well, that might be a bad thing because you might have a computer that's acting as a server and maybe the latest backups for some database or something like that haven't been stored off site or something. So shutting down that computer might be a really bad thing. Right.
How quickly would that kind of program execute? Almost instantaneously?
Yeah, almost instantaneously. Yeah, I mean that's like the ultimate jerk program.
So like, so somebody who is trying to like, in this might be trying to check things that might have just left the terminal open to be able to do that. Is that what terminal is used?
Well, yeah, or you can get a terminal by just plugging into a serial port on some older servers. So there's some other ways of getting around it. But the point is that we're mostly protected against something like this today. But from our perspective here, creating a child process is super simple. And all we're doing here is we're just, you know, couch surfing, just sitting there and waiting. All right, go ahead.
I'm sure
well, this isn't running on the Mac. This is running on their terminal on their.
I'm guessing this is
well, it's not going to kill my computer. This isn't running on my computer. This is running on online GDB's behind the scenes terminal. I'm in a web page right here, right? So, you know, it's sending this code, executing on some terminal someplace else. The problem is actually here, this is a problem I need to, it'll take a long time here. So if I say int PID is equal to that, and if I say if PID is equal to 0, we'll tell the child to sleep. Otherwise, the parent will just spawn another one. So we'll do a spawn child. That would be pretty funny. They're just running on like an old Raspberry Pi or something like that. So eventually we got a child is -1, which is probably protection from the operating system saying this program has generated too many child processes. So your new child has a process ID of -1, letting you know that error, we died, OS cut you off, yada, yada, yada. Make sense? All right. But punchline is creating child processes is super easy. Programmatically, it's one line of code. And like you said, you could just throw it in a while true and just, you know, why be logical when I could just say, look, whatever it's going to take to kill you, do it. Program will crash when you run out of process IDs. All right. And the reason I had to do this in an if is I wanted to make sure that if I was the child, I would wait. Otherwise, I wanted to make sure I looped back around to create a new child. That's why it wasn't running quickly before. All right, so the OS designer decided to represent their process IDs using a short, even an unsigned short. You know, they would be limited to 65,536 unique process IDs running on the operating system at once, and anything more than that would become problematic. These are just decisions that the operating system writer had to make. All right, and that is something that limits us to our what's running on the current operating system. All right, so a process, which now we just saw becomes a problem when we're talking about processes versus threads. So not only are processes heavyweight, take a lot more memory and things like that, they also are dangerous because each time you spawn a process, you're getting a new process ID. Similarly, even if you're not malicious like we just were, and you're not actually spawning off 65,536 processes, what if you just want your program to get extra CPU time? So look, let's keep our numbers in human terms. Let's say your process gets 1 second of CPU time, and you decide, well, I want 10 seconds of CPU time. I don't want my program to have a context switch, get off the CPU, go back and get at the end of the line and have to wait again. I'll just create 10 more processes, subdivide the work, and then then I'll have 10 seconds of CPU time that my things are working, right? No problem. So all of a sudden, the only thing that's running on the computer is your program. If you create enough child processes and you have something that can divide work up. If you can't actually divide the work up, that's where the inter-process communication stuff comes in. You have like this parent process who's handing out work to the children. You do this, you do this, you do this, that type of stuff, so that they can you actually are increasing the performance. Otherwise, you're not actually, you're going to get just as much CPU time as any other process of the same priority running on the operating system. So that's another thing you can do if you write multi-process applications, is you can create a situation of unfairness on the operating system. All right, so threads are preferred most modern programs. Threads allow us, well, let me ask you this. What do they both allow us to accomplish? Almost like, why would we want to ever create a thread or a second process? What problem are we solving by creating a thread or a process inside of our program? Good. Okay, potentially divide up work. Go ahead. Multiple things at once, or at least seemingly at once, right? So it allows us to bypass a blocking line of code and do something else while we wait. for it to finish. Now that comes in with the caveat of the problem we're solving needs to be something that can be done at the same time, right? You know, like the real life example, if you're baking a cake, well, you know, there's a lot of things that have to be done prior to you putting it into the oven. So you can't just spawn off a child process and say, put it in the oven while I'm doing all this other crap. Because then you start missing the pie can, the cake pan or whatever. Go ahead.
So the fourth command started with the text
no, it would pick, actually, it depends on the operating system whether, actually with fork, it would pick up where it left off in the function. It literally picks up what it deals with the program counter, how the process or the CPU scheduler works. If it was a thread, you then need to have your functions be thread safe. And actually, typically the way threads, p-threads work this way on Linux, the way they're implemented is you actually attach the thread to a function. So you leave main, you actually say, here's my function, this is what I want the child to do, spawn off a thread, that's your job. You launch that function and it just goes and does its thing. And when that function ends, the thread dies. Okay, so the problem we're solving is to create situations where we can have blocking code while still doing other things that would make sense to do. And threads are a safe way for a programmer to do this because we can say, look, I'm not impacting other processes on the computer. I'm not making myself more important, right? I'm not possibly taking up all the process IDs of the computer. All I'm doing is I'm allowing my program to do more than one thing, potentially at the same time. I'm at the mercy of how the operating system schedules threads. Because the CPU, if you have a 16-core CPU, it's possible that you have a bunch of cores that are free and it might schedule some of those threads on individual cores. So it actually is happening at the same time. Okay? Even though you were only allotted a certain amount of CPU time, it might just bypass that because processor's not busy. Okay, but you're at the mercy of the operating system of what its job is. The operating system's job is to schedule those things. So from the programmer's perspective, we would say, look, I'm going to create threads because I want various pathways of execution happening in my program as if they're happening simultaneously so that I can have non-blocking things that are occurring and I'll let the operating system handle the details. Because from a programmer's perspective, we shouldn't care about the details most of the time, unless we're trying to crash the system or artificially give ourselves more CPU time and that kind of stuff. All right, so threads kind of fixed a lot of problems for us. But it's not like it solved everything, because how many threads could a single process have? Depends on which data type they use to count the number of unique thread IDs, because you get a thread ID in there, right? So, but now what are you risking? You're risking crashing a process, not crashing the OS. And that's the programmer's problem if that kind of thing goes down. All right. Having said that, we're going to actually be working with processes for a while, not threads, because that allows us to focus on the traditional foundation of inter-process communication, where there's a lot of stuff built into our programming languages for that. But know that there are ways to have threads communicate with each other as well. So it's not like this is, in fact, many of the inter-process communication stuff can be used by threads. Sleep function thing. I brought something up. I wanted to. This guy. All right. So last time we were looking at these various system calls. So kind of the API of our operating system-ish, something along those lines. And now we've kind of seen how the fork system call works, right? And now that's a tool that we can incorporate into our programming if we want to. Now, I think I mentioned it last time, but if you want, use onlinegdb.com. It supports all these system calls that we're looking at. If you have a computer that you want to use your own C compiler or something like that, you can. But you basically, in order to do these things, you're going to have a Linux shell. So you can go and install the bash shell on your Windows machine, but then you'd also have to install GCC on there. I'd say it's more trouble than it's worth, to be honest. So I would use something like OnlineGDB. If you have a Mac, well, you can use a terminal on there that comes with GCC. All these things should just work. Or you could just use OnlineGDB. You can kind of pick your poison. But I'm not going to support a whole bunch of different compilers and IDEs and stuff. So you use whatever you want to use. And when you turn in code, you're going to have to give me a link. It could be a GitHub link, whatever. I don't care where it came from, but don't come to me and say, hey, fix my insert unique IDE here. You don't even have to. You can say save here and 450 process functions, something like that. I'll just name my project. So you sign in here. And so when you save, now you can just say share. It'll give you. You can also download it and put it on GitHub if you want that. That's fine. Okay. Go back to this dude. All right, so that's what the fork system call does. Exit system call, pretty straightforward, makes the process die, process ends. That happens automatically when you get to the end of main, or you can force it to happen prior to that. So it's kind of like the operating system. It's like the system call equivalent of the return keyword. Return keyword makes a function immediately end. The exec system, the exit system call makes this process die. Doesn't do anything else. Okay. Now we have the exec system call. So this is something that allows us to call other programs on the underlying operating system. And as you've seen, I've done several things with this today. It's pretty common in Linux or Unix for us to use multiple programs together to accomplish stuff. That's not something that we're kind of used to doing in Windows, because we kind of think about our applications as almost like, launch a game and that thing's running on its own. Launch something else, it's running on its own. And these two guys, you might say, this guy's going to save a file and then open that file over here to do something else. But we're rarely having the output of this be the input of this directly. We're typically not solving problems with running programs. Modernly, that sort of kind of went out the window once we switched to graphic user interfaces. All right. But the exec command, Linux system call, allows us to tell our program to launch another program on the underlying operating system. And that other program would get its own process ID. So you can say that this is actually similar to the fork system call, except the fork system call actually creates a split of our program where the exec system call launches another program, which could have been another program that we already wrote. Maybe we wrote a program, compiled it down to an executable, and then we launch another one of our programs from within another program using exec. Go ahead.
So is that exact thing like that? It's one of the same kind of attack with exec, like it's not a fork.
What?
Like, how you talk about that attack where they can span a bunch of new processes? That same kind of thing happening with the exec command.
Yeah, I mean, I guess you can call the exec command 65,000 times, and
so and then like operating system protects against that, but generally protecting against any new processes created by that original process.
Yeah, I think this would probably fall underneath that. If you launch an underlying program using exec, I bet you it's linked to the program that did it, that called it. But you're also at the mercy of how long does that other program run for? Because like we saw when I was out here at the terminal, I mean, this was, this is a pretty complex string of events here, right? that I'm running. This is one program running that has an output that I'm piping into another program that runs, but that whole thing's now done. Gave back its process ID to the operating system to use for another process because he's now done. Make sense? All right. Oh, so, and you're going to see this in a second. There's multiple versions of exec. So this guy says running a new program does not require that a new process be created first. So if you wanted a new process to be created, you would do a fork first to give yourself a child process who then would launch an external program through an exec. Okay. Otherwise, the current running program is immediately terminated and the new program starts executing, picks up where it left off in the same context, in the same terminal, same part of the operating system, whatever you were doing. Okay, and that's the same context is going to make even more sense when we start talking about inter-process communication using things like shared memory, because those things are going to still exist in the world that this new program is launched within, so it'll have access to those things. But if you want your program to continue running and some other program to start running, you would need to create a child, then have the child exec. Child dies, your other program's running, but your original is still cooking. Okay. Now, there's multiple versions of the exec system call. Just like earlier when I said man fork. So if you're on a Unix terminal like this, man is a manual page. You can get the same thing just doing a Google search. You can say fork system call or something like that. But this guy will give you the manual page for the fork system call, creates a new process, requires this guy, the Unix standard library for doing it, tells you some information about it. So it's documentation for this guy. If I say man exec, what does that guy give me? I probably would have to do it a different way, but so I did Google that one. And I think this is the thing I got out of it. All right, so we see here that there's a bunch of versions of the exec system call that takes into different parameters. Okay. So this system function takes in the path of the executable binary. So for example, if I type in ls, that's like the directory listing that lists the contents of the current directory in Unix. The equivalent of this in Windows is dir. All right, so if I say ls, it gives me the directory listing. Now, I can type ls from anywhere in the terminal because ls is in my path. But if I say which ls, it's going to tell me where does that program actually live, and it's probably going to be in /bin. So in the operating system, in a POSIX-based operating system, we have a directory called bin that typically has the operating system's binaries, the executable programs owned by the operating system, and ls happens to be in there. If I say echo, what's it, $ path? No, it's % path. $ path. There we go. So there's a system variable, an environment variable called path, and this is all the stuff that's in it. And the way the terminal works is when I just type a command like this, it checks all these places for that command before it comes back and tells me I couldn't find it. So here, I'll just make up that guy's not there. It just checked all of these different possible locations, possible places that are in my path that I wanted to check, looking for that executable. Okay, but I can always give it the full path of the program. I don't have to rely on the operating system, in this case, the shell program, figuring out where it is by looking at all the places that are in my path. All right, so this function, the exec L, go ahead. Yep. Yep. It's because and you really what you're talking about is on Windows. Because typically, if you're installing a user program on Linux, it'll put user programs in /user/bin, which is already in the path. But like you mentioned, if you're installing a Windows program, user programs tend to live in their own directory. So if you want that program to be able to launch from the command line, which checks the path variable, it'll add it to on Windows. You can type in environment variables. Maybe it'll take you to some GUI for managing your environment variables. And one of them is called path, and you'll have a whole bunch of things in there. So it'll add those individual directories to it. But that's only going to be important for programs that you intend to use from the command line. Otherwise, you don't need, just double click the icon, good to go. All right, so this function takes the full path of an executable binary file. So for instance, something like this as the first and second argument. Then the arguments, so this is like the things you're going to pass to it. So this is ls-lh. So this is going to be a, I don't know what the H command does. So it shows symbolic links, unless there's a lowercase h. There is. Oh, this formats it a little bit nicer to the screen. So these are command line options for ls. So as we're filling it in, we just come down here. We'll just look at the code. So this guy, in fact, here, let's just put it in our program. All right, so I hate when they format stuff like that. It's just garbage. So here's a variable that's going to hold the path. Here's one of the arguments, that guy. Here's another argument. So these are just 3 old style strings. Now we're going to call that exec L, giving it the full path to it twice. The first 2 parameters of the full path, I'd have to see what they're calling them to give you a rationale why the first 2. One of them is probably just the string for like, if we were to print it out what ran, it would show you this is the command you issued. The second one probably actually processes that path and gets to the executable. And then you pass it the arguments that you want it to take. Because the typical format for a Linux command is command name, followed by arguments, command line arguments, those dash, LH, blah, 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 followed by the destination, the source, the thing that's required as input, usually a file and a POSIX-based operating system. All right, so we're giving it what I wanted to do, what special options, what am I doing it to? You run this and we should get the output of calling ls-lh on home. Now if I want to, let's see how much we have access to. Yeah. So now we're seeing we have a full Linux install behind the scenes here. That's not on my computer. If I want to go into /bin. It doesn't let us see /bin. Yeah, so now we're seeing all the user accessible programs that are in there. Oh, so they're running X Windows on this. So we're actually using this would actually be a pretty good tool. one of the hard things to get access to, in fact, we're going to write this maybe next class, but soon. One of the hard things to get access to anymore is actually getting a Linux terminal to practice stuff. If you're on a Mac, you have access to one. But if you're on Windows, you don't really, except it's built in. I think it started, didn't we say that's Windows 11 includes it now? But a lot of times it's hard to get a terminal. Well, nothing keeps us to just having an infinite loop in our program that has you type in whatever command you want, and it just sends it using execl behind the scenes. Actually, we can just use one of the other execs that just uses the path. So we just fake. we fake a terminal by just passing the buck. Pretty interesting thing. Okay, so questions about any of those things we've looked at so far today? Okay, so I'm going to put up an assignment dealing with the fork system call. Won't be, horribly involved, but enough to get you using it a little bit, write some code. I don't care what thing you use to write it. Online GDB is what I'm going to do all of our examples with, and you'll turn in the link to it. But I would call it a relatively light programming assignment just to get you used to using the libraries and make sure that everything's working for your development environment. Sound good? So I'll put that up sometime today. All right. Questions, comments, concerns, bribes. I'll see everybody on Tuesday.
Thank you, Professor.
Yep. You have a good one.
You too.